welcome everyone. So you think we are recording? Great. So it's my great pleasure to have here Megrelishvili from Israel, who will have this mini course, this series of lectures every day this week about representations of dynamical systems in Banach spaces. Okay, so please, we want to learn things, so please interrupt and ask questions, and let's try to follow all the details.
Thank you very much. Thank you for coming, and thank you for the organizers for this wonderful opportunity. It's my third time in Warsaw. I enjoyed it here very much. Last time, 1 year ago, during the conference, it was very useful for me. Very nice, very well organized conference. Thank you to Piotr for inviting me. My first time, by the way, it was I emigrated in '91 from Georgia, from the Soviet Union, to Israel. And my way was via Warsaw. I was one day in '91, 20th of March. And so it's a very historical place for me, very, very important. It's now I see it's also for other reasons, very good reasons from mathematical point of view. So thanks again, and I will try to show some ideas, results around the Banach representation of dynamical systems. And first of all, let me mention that I will expose some results which are joined with my co-authors, colleagues. First of all, Eberlein from Tel Aviv University, and also some results are joined with Professor Vladimir Uspensky from Ohio University. Okay, let me start with some introduction. And what is the field, the real field of this investigation? And we are speaking about dynamical systems, so it is obvious that the dynamical system is one of the main objects of this theory. But what else? The second main object is, of course, again Banach space theory, and we try to use the depth and powerful tools of Banach space theory to explain something, to solve some dynamical systems problems, and vice versa. And we will see that sometimes some known facts in dynamical system can help to produce some good examples of Banach space theory on some effects and maybe even some new definitions. So we have some interrelation between two theories. And the idea is to use this interrelation systematically to give some hierarchy of objects, like topological groups and dynamical systems, and hierarchy of Banach space in Banach spaces lead us to the hierarchy in dynamical system theory. And the main class of nice Banach spaces we will explore. These are the following classes: reflexive Banach spaces, and actually also Hilbert Banach spaces, Asplund Banach spaces, and Rosenthal Banach spaces. Of course, we will explain, we give corresponding background and definitions during my lecture. And in the beginning, I would like to pose some questions, something like motivation, why we need it, why it is exciting for me. And then I will go to some background material, which I hope so will be quite self-contained. By the way, technically you can follow my lectures also by my website. You'll see here my homepage, but you can capture also the direct address here. So you can download my lecture notes and also some exercises related to this material, and as well as some old or not so old papers which are closely related to our object. So it's, I hope it would be useful for you. Of course, you can ask questions parallelly, interact with me, and so on. And another way, of course, you can of course send me emails, and we can exchange some emails and answering your questions. And what kind of questions we are looking for, and what kind of questions we emphasize the main question. And first of all, some intuitive questions to provocate this to understand what will be main direction of this investigation. And what is the common between a Radon-Nikodỳm property, a weak almost periodicity in the dynamical system theory, and reflexive Banach spaces? But this question is quite old and even well known. It is not new in our investigation, but is only partially, even in this case, we had only partial results, which comes actually from Eberlein. Second question, what can be interrelation between a lack of butterfly effects, some chaotic dynamical systems or non-chaotic dynamical systems, and the Asplund Banach spaces? And when we are speaking about Asplund Banach spaces, actually maybe that is the time to give first definition. What's the Asplund Banach space? V is an Asplund Banach space means one of the equivalent definitions, of course, for every separable subspace, the dual remains separate. The dual we denote it this way. And this class of Banach spaces is one of the mainstream classes in many years, and also today. Okay. The next question, which we are interested to understand, what can be linked between something like Fibonacci binary sequence? I will explain what is this. Quasi-crystals in physics and some new directions, monotonic maps, and Rosenthal Banach spaces. What is Rosenthal Banach space? Rosenthal Banach space, in contrast to definition of Asplund Banach spaces, this name is not so familiar, but this class is very well known after Rosenthal's famous results. As we say that V is a Rosenthal Banach space if it doesn't contain a copy of L1. And it is quite immediate that Banach spaces. Of course, every Asplund Banach space is Rosenthal. Because you know the dual of L1 is L infinity. So immediately we get this inclusion. Okay. And now what I mean to provocate, you know, something in order to provocate your interest and avoid some boring sequence of definitions. Sometimes it's a good to give some exams like Fibonacci sequence. What is Fibonacci sequence? If we consider, you know, some line with slope, some irrational slope, but in this way you can. I take some very partial case with a golden ratio. In this case, we can define sequence in very natural way. It's well known in number theory and dynamical system theory also. Is cutting sequence, cutting binary sequence. What is the algorithm here? So we meet the, you know, this vertical line on integers, integer lines, horizontal and vertical, and red one is 0, so vertical line, and we intersection with horizontal line, we sign by 1. So in this way, we obtain a sequence of zeros and ones. So some binary sequence. And one of the interesting questions in many areas is to understand how complicated can be such sequence, not only for this particular case of slope, but in general. Take some, of course, irrational slope in order to get some good dynamic and some not so simple sequence. But if you want to understand how complicated is this, you need tools. What's your meaning? So one way to see is to see this sequence in some dynamical system. I mean shift system, or Bernoulli shift system of sequences, considers a shift, and you can consider the corresponding orbit of this sequence. Then go to orbit closure. Orbit closure will be some dynamical system, compact subshift of Bernoulli system, and you can try to understand how complicated is this object. Okay? But it is quite, okay, this is one direction, it's very well known, it's symbolic dynamics. But we can ask another question. The question which will lead us to understanding why I am asking about Banach spaces. So the question is, how can I represent this sequence by tools of Banach spaces? I mean in the following sense. First of all, the Fibonacci binary sequence you can define also by this rule of substitutions. What I wanted to also to mention here, maybe something. Yes, maybe some general question here. So this sequence is something like this, right? And actually we have natural numbers and some binary sequence. Okay. So we have some sequence CA. And we want to understand what happens here. As I mentioned, you can look at, part of the Bernoulli shift system is just topologically just counter Q, and we have the shift by N in left side. And this way we have some dynamical system. And if you have some C, we can consider his orbit closure. It induces some subshift. Let me denote it by XC. What is XC? Take a C and we need to spell NC and the closure. Okay, so we have some point. At some stage we consider the corresponding orbit into a counter cube with a shift, and look at XC. It's some dynamical system. But we can do it in many other cases, not only for N. Just take here a Z, for example, or some any discrete, even discrete semigroup or discrete group, and we can obtain some similar object. This is one way to have some binary sequence. Okay. And we see here only particular case. Another case to get a binary sequence which is related to Banach spaces. This is the following possibility. Take some Banach space from some nice class of Banach spaces. Now consider some vector, some here, F from the dual. Consider some sigma, maybe some isometry or some linear operator is not greater than 1. For example, it can be some isometry. And now we can consider the corresponding matrix coefficient. And what is matrix coefficient? After we have some sigma, we can go to the corresponding iterates. And in this way, so if our iterates are positive, in this way we have the following function, not necessarily binary, just some tutorials where for every n we consider like this way Cn will be generalized matrix coefficient. Take iteration of sigma, nth iteration, its image at V, and corresponding evaluation map. The standard evaluation map by linear mapping. Of course, we can write it also in this way. Again, it's matrix coefficient, and one of the interesting, in my opinion, question is what might be connection or what might be link between 1 and 2. So it turns out that this question, what kind of question? When some abstract binary sequence we can represent this way when our V is in some nice class of Banach spaces. And in our case of Fibonacci sequence, it turns out that we cannot do it in a reflexive or even Asplund Banach space, but we can do it in Rosenthal Banach space. And of course it is not there are many other examples. Just my choice of Fibonacci was, to provocate the interest. But in many cases we found we can obtain some general theorem when we can do it. This kind of question brings together some tools, dynamical systems, topology, general topology, and Rosenthal Banach spaces. And below we see that one of the main ideas and one of the main tools will be fragmentability in Banach space theory. Fragmentability, in fact, is some topological concept, but it was born in Banach space theory. And it's very effective for, first of all, for Asplund Banach spaces. Just we can reformulate the definition, but we will do it later. But also we can reformulate in the definition of Rosenthal Banach spaces with some kind of fragmentability, which we call eventual fragmentability. So now I speak about the continuation of my lecture, some kind of plan. What about other questions? So here, I put here also some much more elementary sequence, just zeros, and at some stage start with ones. It turns out that even this sequence, and we will show it in full details in both cases, that even in this very elementary sequence, you cannot represent it in reflexive spaces, but you can represent it in Asplund spaces. And we will see the reasons why it happens. And with any Banach space, we can associate several, yes, so I already mentioned our connection with nice Banach spaces, and there are several good reasons why we are speaking about reflexive, Asplund, and Rosenthal. That means that we cannot consider other classes, but at this moment, in this theory, we have good results only for these classes. Okay? Of course, some results for Hilbert Banach spaces. Okay. One of the main tools, it should be mentioned even now, in this theory, will be famous factorization theorem by Davis, Hegel, Johnson, and Belczynski, in order to construct some Banach space from prescript class, from a nice class of Banach spaces. We need some kind of DNA data which contains some starting points and it looks like something. We have some compact space and some family which separates the points, but this family is good. In some sense, this family is small, and according to this, we can construct, again, using Davis, Hegel, Johnson, Belczynski, good Banach space. And we have some kind of remedy when we get, of course it is not our results, very well known and now classical results of Davis, Hegel, Johnson, Belczynski, but we have some dynamical adaptations and some non-trivial points for dynamical systems. Okay, during our lectures, we will see the following. Among others, we will see some known results. Of course, we need it because besides some new results, we need also to obtain some soft proofs, some new proofs, some short proofs of non-classical results, like Telemann's representation for topological groups. I will explain Ellis and Ellis-Lawson theorems about compact semi-topological groups, and Helmer's theorem about Megrelishvili periodic functions on topological groups. The theorem is that every weakly almost periodic function on any topological group necessarily is both right and left uniformly continuous. Once it was a famous question. Of course, one of my favorite applications is Riemann-Narzeski fixed point theorem. Actually, we can reduce the proof to some other results which belongs to Fürstenberg. That is the idea. So something like half of the proof we can do it in 2 lines or 3 lines using the idea of fragmentability and lifting the actions and so on. Now, again, some concrete questions, and to every Banach space, as I mentioned, we can associate several structures, and this gives us possibility at least ask some questions, but we can see also that we can also some good answers. Okay, let V is a Banach space. At this point, we have no restriction, and so what we can do immediately, we can this way the dual Banach space, but many times we consider also weak star topology, and P star is the unit ball in weak star topology here. So, as usual, it will be in weak star topology. By B, we consider we denote just a closed unit ball. Okay. Of course, by a standard Alaglu theorem, B star is a compact space, and same as every bounded closed subset is also compact. And we can ask when our compact space can be embedded into B star. So at this moment we explore the fact that B star is a compact space. And this kind of question is very well known, in fact, because if we worry, consider here, let me start by maybe reflexive Banach space. This way we get the definition of Eberlein compact spaces. For Hilbert, this will be uniformly Eberlein. For V being Asplund, Radon-Nikodỳm. Okay, but last time we tried to understand also weakly Radon-Nikodỳm, just the case where now